My name is Piotr, obviously, and I'm here to tell you a bit about NATS. What is NATS? At its core, it is an example of messaging system, so something similar to what Apache Kafka or Apache ActiveMQ provides. It allows you to send messages from one component, one software component to the other. But it does it in a very peculiar way, as I'm going to show you in a second. Initially, the software has been written in Ruby, and then later on, it got rewritten in Go for performance reasons. It is open source with Apache license, which is pretty liberal. No, that doesn't help. The source code is available on GitHub if you want to contribute. Now, how does it look like internally? Initially, NATS has been developed as a component that is currently called core NATS, which can be described by a list of properties that will be covered on the next slide. And then as an evolution, so to provide features that were not really available at the beginning, the jet stream is the logical next step that builds on top of core NATS and introduces some more guarantees. So core NATS has a very specific property that it only guarantees at most once delivery, which effectively means that if you have clients that are listening to a specific subject or topic, then they are guaranteed to receive the message. However, if there is something wrong going on, if there is a connection drop on either side, the message-oriented middleware itself is not going to guarantee any message redelivery or any other guarantee on top of that. It has its use cases, as I hope to show you in a moment. And it can be described as a publish-subscribe broker with some additional features built on top of it. Publish-subscribe is the most commonly used use case, where it allows communication between a number of components on the producing side with a number of components on the consuming side. If we already established that functionality, we can provide some more. And request reply is one of the features that actually utilizes publish-subscribe in the way that they add a single field which is dedicated to retain the reply address. So if you send a message, say that you would like to pass some notification to your client, you then sign your message with your own identifier, unique identifier, which then can be used to send an acknowledgement or any other type of reply. Something else that also utilizes the publish-subscribe communication channel would be queue groups, which is also a method of communication that other types of message brokers use and allow developers to use. And it consists of having a number of consumers, so clients that subscribe to a specific topic to receive messages, but they constitute together a single group. And within this group, every single message that is incoming will be consumed and processed by a single component. So naturally, it can be used, for example, as a client-side load balancing. Then Jetstream is an extension of core NATs in terms that it allows or guarantees at least once delivery, which means that there is some internal buffering going on the broker side. And in case of any temporary network problems, for example, the message will still be delivered to all the interested parties. One caveat, one major caveat, is that it is built on top of core NATs, which means that if we achieve a certain level of performance by using core NATs, then we shouldn't really be expecting anything better simply by switching to Jetstream. We are going to get some additional features, that's for sure, some additional guarantees, but performance-wise, we should not expect any huge improvements or any improvement at all. And this talk is mostly focused on, or entirely focused on, core NATs. One major property and the philosophy that sticks behind every single aspect of NATs seems to be the simplicity. So even if we take a look at simple architecture, except from being very elegant picture, it pretty much applies to any other message broker. If we replace NATs with Kafka, we effectively have the same diagram. Typically, we have a client application, either producer or consumer. We have the message broker. Here we have NATs, and there is a connection, a network connection between them. With NATs, all these connections are TCP, so we already get certain protocol guarantees, which also come at a cost. Now, the single node architecture is not really fancy or interesting, but we can pretty much free of charge combine a number of NATs instances into a cluster, and then the message passing within the cluster is already handled by NATs itself, so we don't really have to worry about that. We can start clients connecting to different nodes, and then the internal message passing is going to be handled behind the scenes. The next thing that shows the simplicity that has been applied to aspect of NATs can be the protocol itself. First of all, it is text-based, so not really the most performant as we can think of, but it has the property of being human readable, which helps if you want to debug your messages on production, one way or another. It only defines a very small number of messages, which also guarantees that the client that implements the protocol can be simplified to the bare minimum. Within the single message, we can have a number of fields. They are separated by spaces, and then each message is terminated with carriage return and line feed. So very similar to what we used to have with HTTP 1, for example. Since this is a client-server architecture, we have a set of messages that is dedicated to client side, and then server has its own set. When it comes to client-to-server communication, there are a number of messages. So clearly the one that would be very interesting for producers would be to publish a message, which is a pub message. Then at some point, when NATS 2.0 has been released, a new feature was introduced to support headers, message headers. So then we also have HPAP to publish message with headers. We can subscribe to a specific topic or subject, and then we can also unsubscribe. Then there are messages that are not really payload oriented. We can issue a specific connect to the server, and there is a heartbeat mechanism which is implemented as a ping and pong messages. On the server side, we have something similar. Every message that is published is transferred to subscribing clients as a MSG message. If subscribing clients and the server itself support headers, then we get the H MSG message. And also we got the acknowledgement or the negation of acknowledgement. Not really the most efficient either, because we can see that only the first character would be sufficient. However, this makes it more obvious. And when it comes to messages that are not payload oriented, we have the info message, that is a reply to the connect, and the same heartbeat mechanism as has been shown for the client side. So we already grasped the overall architecture and messages that constitute a protocol, the protocol. So now it's high time for the demo. Let's see how that goes. Okay. So first we are going to start a NAT server. We are going to run it in an interactive mode. It will be removed when we close. We are going to give it a name, and a single port is going to be exposed. This is the default port that NATs operate on. Of course. Sure thing. So once more. Right. And since I mentioned that the client can be that simple, we are not going to use any client at all. We can use the network tool of our choice to connect to NATs. The only thing to remember is to use carriage return and line fit as separators. Netcat doesn't provide that by default, so we have to configure that. Okay, and we can already see that we received the first message from the server saying, this is my ID, this is my name, I support headers, this is the maximum payload that I support. So we can subscribe to a specific subject. Typically life is miserable enough that we can make it more happy or entertaining, so we subscribe to jokes, and then we provide an identifier. It can be an arbitrary identifier, anything of our choice. The thing is that if we subscribe to the same subject again, using the same identifier, it should indicate that this operation does not succeed, but it doesn't. And this doesn't mean anything at all. The identifier should be unique within the single connection, and if we have more than one, NAT server is going to treat it as a single connection or single subscription. We can also connect to that same server from another client. Let's also subscribe to jokes with the same identifier, because why not? And now, let's produce a message. Jokes. Now we have to provide the length. This is the limitation of using the network tool. Okay, so why did the two Java methods get a divorce? And luckily we received the same message in each client. And we can see that even though we subscribe to jokes twice with the same identifier, it effectively means receiving the message once I'm not going to answer that question yet because there is another demo where we can use more than one server instance. So let's do that now. However, before we continue, I'm going to show you the configuration. So when we configure the cluster, well, this is pretty boring because this is going to be the first instance. We will need to define routes. So there is going to be a route between the second instance and the first one. It looks like this. The internal port for NAT's communication between the nodes is going to be at the default port, which is 6 and then 222. And we are going to use the same cluster name in both cases. So let's start the server. Let's start another one. Okay, and we can see in the log that there has been a route that was created. We expect the same message to be printed in the first from the first NATS instance. That happened as well. So right now, what we have is a component called NATS1, which is running on my local host on the default port. Then we also have the component that is called NATS2, which runs on port 4223. So let's try to connect to these two instances now. That would also be netcat. Right, let's subscribe to JUG again. And now let's connect as a producer. Okay, so before the question was why did the two Java methods get a divorce? Let's try to publish an answer. Hopefully that's the length. Because they had constant arguments. Cool, and this excellent answer has been received by both clients. So we can already observe two conclusions. First is that these jokes are not really funny. And then the second one would be that internal communication is working as expected in the cluster environment. Now, if we decide to kill the second instance, we can see that only the client that has been connected to it has shut down. We can still maintain the connection that has been established to the first instance, which helps if we want to scale horizontally. Now let me close unnecessary clients and move on. So we already know what NATS is. How does communication using NATS look like? Now the follow-up question would be, why would I even want to use that? And one of the answers can be performance. And when we talk about performance, benchmarks help a lot. Unfortunately, when it comes to core NATS, there is only a very limited set of benchmarks available, because, as mentioned before, The jet stream is a more recent technology, and it provides more strict delivery guarantees, so it naturally attracts more people. But as I'm going to describe, even core NATS has its use cases. Now, this benchmark is something that has been published online. It compares a number of different message-oriented middleware components. Here we can see comparison between NATS and RabbitMQ, where two types of messages have been sent or passed around. The first one was rather small. It was 1 kilobyte in size. The other one was 5 kilobytes in size. And during the time of the test, there were 3,000 messages being published constantly. Unfortunately, the benchmark does not specify how many clients were subscribing, so we don't really know how many connections were receiving the messages. But we can already see that somewhere between second and third percentile, there is the performance hit that pretty much both components take, with drastically deteriorating when it comes to RabbitMQ. NATS looks pretty much okay in this very simple case, and it maintains a single-digit milliseconds. It gets more interesting when we compare different solutions, different middleware solutions, with more messages flying around. So in this case, in the more demanding test, there were 20,000 messages being sent. And we already know that there were 25 concurrent connections subscribing to these subjects. In this case, only a single payload size was used. That was 1 kilobyte in size. And comparison shows NATS against Redis, where we also see that somewhere between second and third percentile, 9 percentile, the performance deteriorates. What we can see is that NATS is slightly better than Redis in this case, and it deteriorates up until 80 milliseconds of message latency. Now, it's all great. Typically, benchmarks tell one side of the story. Now, how would that look like in production? So at IMC, we used to have a couple of problems when it comes to message passing. One of them could be described as a throughput-sensitive scenario, where we had a high number of messages being passed in somewhat short time, and we wanted to make sure that all these messages are going to be transferred correctly without causing any problems either server side or in producing / subscribing clients. In this particular case, latency was not a primary concern, but it was also somewhat important. So we wouldn't like to replace existing technology with something that can handle more load throughput-wise, but would cause latency spikes. Initially, we decided to go with Kafka, so as at least half of you, which was a sane solution at that time, because we already had some exposure to Kafka. We already had Kafka clusters. So we decided to start the implementation. Initial tests were pretty promising. We were able to handle the load with roughly the same latency. We started noticing problems very late, because only in production, where not only was the initial latency, well, not initial, but the latency with Kafka was worse, there were also some strange allocation patterns that caused clients to allocate more memory. So we started digging. There was a dedicated test extracted from our main scenario, where we try to reproduce what the problem is. We were able to measure publication of 1 million messages between a single producer and a single consumer, and to see how long does it take with our solution that we used to have at the time, which was Hornet Queue, one of the JMS implementation. And we also measured how much allocations do we observe in total, so both producer and consumer side. Then, since we already had the implementation, we did the same test with Kafka. And these numbers are not really representing what we got, because initially both latency and allocations were worse. So we had higher latency and more allocations. However, it was not more than with Hornet Queue, allocations-wise. So we didn't really, the artificial test that we performed didn't really tell us the full story, because we already saw more allocations in production clients. But what was clear was that the latency of sending messages with our infrastructure was worse with Kafka. So we knew that we cannot really proceed. We already had all the plumbing classes required to migrate from one solution to the other, and a suggestion was made to try out something else. At that time, NATS was somewhat promising performance-wise, so we decided to give it a go. Since it is a very simple client as anything else with NATS, we had to provide some additional scaffolding, including message serialization. We didn't use something that we used to have with Hornet Queue or with Kafka, and the results were very promising. The time it took to transfer these messages was significantly shorter, and allocations were 3 times less than with Hornet Queue. So at that point we tried to reuse the same serialization method with Kafka, just to compare the thing that we were interested in, and just that. And we got the numbers that you can see on the slide. It was still allocating more than NATS. It was better than JMS, but latency was where the crucial difference has been found. At that point, we decided to go with NATS, and so far we observed rather promising results. In this particular scenario, so mostly throughput related, where the latency is not that critical, but still important. We currently serve 18 billion messages per day on the incoming side, with a small fan out resulting in 60 billion messages being passed around every day. On average, that gives us 750K on the incoming side and nearly 2.5 million messages on average per second on the outgoing side, with bursts oscillating at 1.5 million and then 4.5 million respectively. And this is all handled by a single NATS instance. In our other use case, which is where latency matters more, we have a lower volume of messages. We typically have around 6 million events per day. These are not directly translated into messages, because we also have additional fan out plus some more technical messages. We do have roughly 200K subscriptions. Then these subscriptions are not the same. Some of the subjects are more popular than the others. And the numbers, as mentioned before, are a bit lower. So we currently have 18 million messages. On the incoming side, with a bigger funnel than before, but still resulting in 350 million messages. Now, we have different message patterns, so to speak, in this second scenario. So the latency-wise, well, I would like to say critical, but it's not that critical. It's more demanding, let's say. One of the patterns is multiple producers and single consumer, where we record our latency, and something that is on par with the benchmarks that I showed you before. We have recorded below 100 millis latency with all the messages that were shown on the previous slide, with more than 39th percentile. And it gets even better when it comes to well, lower percentiles, with 99 point whatnot percentile recording messages with single-digit millisecond latency. Okay, so since this is a Java meetup, and we have a number of Java applications at IMC, I'm going to show you how to use the official NATS Java client, which is also open source, and the library is called nats.java. So first, as a core principle of NATS has always been simplicity. So if we want to connect to a given NATS instance, all we have to do effectively is to provide the connection string. It is a very simple method, static method, that allows connecting to either single instance or multiple ones, if we prefer. But it has its drawbacks. So in this particular case, we are going to connect to the Docker container running from the same Java process. And if we want then to inspect current state of connections, we can see that we have indeed a single connection that comes from a Java application. This Java application uses library with this particular version, but we cannot really tell much. So if we have thousands of such connections, we wouldn't be able to tell them apart easily. Oh, come on. So this is where options come into play. We can define what is called a connection name, an arbitrary string that should be used to identify the connection from the client application. In this case, we are going to connect to an external instance, so let's make sure that it runs, should be fine. Looks good. And indeed, we can see that there is a single connection with a name that we assigned. So client 1 at a host name. The next interesting thing that options provide are callbacks. So we can have listeners or callbacks that we register to react to specific events. We can define custom error handlers, or we can listen to connection events and react to it. This is what we are going to do right now. Let's stop the first client. Yeah, so we can see that we already received 2 notifications. First, that there was a server discovered and then that a connection is open. So now if we kill the server, we promptly receive messages both in the connection listener and in the error listener. Let's stop this application now and see what we got. So when the first problem happened, the notification said that an exception occurred. We were not able to read from the network socket. And then a follow-up connection event was received saying that our connection has been disconnected. What we can observe here is that both callbacks use the same thread to handle these events. First of all, it doesn't have a very helpful name. So if we have more than one thread pool in our application, it can be somewhat daunting task to go through all the existing threads, picking the one that is responsible for event handling. And unfortunately, we cannot really provide an alternative for that, not with this current implementation of the library. But also there is a problem that if handling any event takes time, all the other ones are going to be queued. So right now, let's start the server again. And create another client that will be handling events in a somewhat inefficient manner. So each event is going to be sleeping for 10 seconds. And now when we restart our server a number of times, we should notice that these events are not really handled in real time, but they are effectively queued. So if we decide to implement events ourselves, we have to keep in mind to either handle these connection events in a more robust way, or be prepared to experience some additional queuing. I already showed you the max payload. That is one of the properties of the information received from the server. And what it means is that NAT's server is prepared to handle only messages up to a certain level. If there is a message that is bigger, then we expect the client to detect that. Let me show you an example. So here we are going to be connecting to a Docker container with a specific configuration. Where we have a maximum payload of 1 kilobyte, and there's going to be an HTTP port to inspect connections. Here we are going to create a simple message consumer saying that it received a number of bytes and then count down on a latch. And then, using the same connection, we are going to publish message to the same subject, which contains 17 characters, but it is repeated 1,000 times. So it definitely exceeds 1 kilobyte in size. As an exercise, you might try to read that out loud. It's always fun. So let's try running the test. And perhaps before that, can you tell me what would you expect the application to do when we try to breach the limit? Any suggestion is good. Just shout out or I will be waiting. Truncate, yeah? I mean, that's one way to do it, right? In principle, I would expect anything to happen. That's always good. However, with this particular test, I think that nothing is going to happen. And this is not great. So here we got an assertion failure saying we expected that latch to be counted on, but that didn't happen. And we cannot really see anything wrong going on. And this is not entirely library's fault. I cheated a bit. I used an error listener, which is an interface, but it also has a list of default methods saying that if you are going to use it like this, it's not going to do anything on a particular error. If we, on the other hand, decide to override a number of messages, we should be able to see that there is something wrong going on. So the test also failed, as expected, but right now we can actually see that, first of all, we violated the maximum payload, and then the connection was closed promptly. Something to keep in mind that it is possible to misuse the library. It can happen if you start using a specific interface very early on in the in a release that was early enough to not define a number of messages. Then the interface evolved, added a number of messages that we simply didn't handle. When it comes to message-oriented middleware in general, there are many problems, of course, but there are two main families of problems. On one hand, we have fast producers, and on the other one, we have slow consumers. So fast producers would be a big spammers, components that send out too many messages for our existing middleware to handle. And there are some options of dealing with that in NATS, in the NATS library even. First of all, we do have options where we can say that we would only like to store a number of messages in our outgoing queue. And then if we breach that limit, application is going to stop. Since this is not really a graceful shutdown, we also have an option to discard messages whenever our outgoing connection, outgoing queue goes full. And this was actually added by one of our colleagues from IMC in order to improve existing library. Now, how it looks in practice. Let's start with limiting the number of messages in our outgoing queue. 5,000 is the default value, but we are going to use it either way to paint the picture. In this case, we are going to publish 100,000 messages, and we expect the listener, the consuming client, to receive all of them. In order to simulate one of the clients being fast producers, we should also overwhelm NATS in one way. And it is possible by simply creating many different subscribing clients that will be receiving all the messages. So if we do that, and then we have messages that are big enough, we should be able to simulate one of the clients being fast producers. or not, apparently. It's always fun when things do not work out. In that case, let's try limiting the number. Well, that's a relief. So we got the error saying that the producing queue became full, and we do not know how to handle this error correctly, causing the application to stop. Ideally, this is something that we do not do in production. In a situation where we have fast producers, it should be acceptable to discard messages that are unwanted. Might not be the case in other scenarios, but in some situations it is, or it should be possible to simply lose messages, but keep on going. And if we do the same test with the additional option, saying to discard messages whenever the queue becomes full, we can see that there is a callback being triggered with an indication of how many messages are actually discarded. And we can see that we are discarding more messages than we receive. Then, more common problem are slow consumers. So, clients that do not reply timely to requests sent by the NATS server. Here we have two different options. We can either handle the problem client side, for example, by using the error callback, or limits that are configurable per dispatcher, which is a consuming piece of code. It is somewhat easy to mimic a slow consumer that will be detected by the callback by one of the listeners. So if we define a listener to simply log a message saying, I became a slow consumer, and this is the number of messages that have been dropped, it should be sufficient to simply introduce a pause in the reading loop. If we do that and try to send 1,000,000 messages, we should be able to see the log output. And indeed, in this very artificial test, we can see that the consumer realizes that it became slow, and a number of messages has been purged from the incoming queue. Another option, if we cannot really handle dropping messages client-side, would be to use the pending limit that was shown on the slide. It has two values. One of them is used to define how many messages we are going to keep in a pending state, or how many bytes are we prepared to handle. If we reduce these both limits to 0, it effectively means to queue all the messages. If we repeat the same test, so sending 10,000,000 messages, we can see that first of all, application should not log any errors, even with the same error handler. And then we should also be able to tell that it is not magic, that we are actually shifting the pressure somewhere. Okay, so 10 million messages have been sent. Now, if we print the class histogram, we can already see that there is no magic. We simply queue all the incoming messages somewhere in memory. So we put more pressure on our heap, and we have to keep that in mind. Nothing is for free. Bigger memory only gives us a certain time to handle the error. On the other hand, we also have an option to detect slow consumers server side. So sometimes an application becomes slow because of something that is not really cannot really be controlled by the programmer. So let's say that we experience a long garbage collection pause or a very long save point. If that happens, or if we are behind a somewhat slow network, there is a concept of write deadline, which is a property on the NATS server. However, to demonstrate that, we have to use some more sophisticated setup to mimic the slow connection between our local host and local host. We have to introduce a proxy that simply adds some latency to all the incoming messages. And if we start such a test, we should observe that it was the server that actually reacted to the scenario. Yeah, if only I run the actual test. Once again, should get disconnected by the server. This is the one. Okay, so we can see that there is a lot of going on, a lot of messages being published, only some of them being received, and then at some point the NATS server that runs from within the container logged a very ominous error saying a slow consumer has been detected. The write deadline of 1 second, the one that we configured, has been exceeded, and then the connection has been closed promptly. The thing is that since this is an artificial test and we simply delay all the incoming network packets, we didn't really detect any connection events either. Typically, what happens in an actual scenario in production, we would expect a connection event being detected client side and then a message being logged saying this connection, my connection to the server has been closed abruptly. However, it is still very nice that the server can detect such occurrence and handle it perhaps not gracefully, but successfully. Now, this is all great on paper. However, we did have a problem in production where a single slow consumer caused message delays in all the other clients. So we had a single misbehaving client that was not capable of receiving messages timely. And what we observed was that other consuming clients also reported significant delays when it comes to message delivery. It was not really evident when a very small payload was used. So in one of our artificial tests, to verify this scenario, we simply passed a timestamp, which is 8 bytes, and we couldn't reproduce any error. However, it became almost immediately observable with more production-grade messages. In our case, these were more or equal to 1 kilobyte in size. The issue has then been fixed with our small contribution. We didn't fix it ourselves, but we helped diagnosing the problem by providing very specific failure scenario. And then coincidentally, someone else from out there in the internet popped in to report that they also observed the same problem, and they were curious enough to dig into the Go code base and pinpoint the actual problem, which was that upon receiving the message, NATS, the server NATS, checks matching subscriptions. So we can have, first of all, a very basic routine saying, I publish to my topic, and there are clients subscribing to this topic. But we can also have wildcards saying that we want to subscribe to a entire family of subjects. So NATS handles all these features server-side, and when it finds a magic subscription, then it sends the message directly from the producer's read loop. So there is a loop reading messages coming from a producer, and if NATS is fast enough to select matching subscription, it tries to send the message straight away to shave some milliseconds. As a safety measure, there was a time budget used, saying you can spend at most this amount of time trying to publish messages from this read loop. And in that case, what happened was that the connection from the slow consumer got or resulted in the TCP buffer in the NATS server responsible for this communication channel to become full at some point. When that happened, then the TCP write would end up blocking, and this blocking took up to write deadline. So the solution, the effective solution, was to remove the time budget entirely. Now, I used to have an example of that as well, has the slide, but we are already past time, sorry about that. So just to summarize, a couple of things that should immediately pop up when we think about NATS. First is that it only guarantees at least once delivery, so something to keep in mind when we jump in to replace every single Kafka usage with NATS. Don't do that, at least not immediately. Then the second thing is that since the protocol itself is extremely simple, it typically results in a simple client implementation, which means that we can achieve great performance if our use case matches the expectations. And unfortunately, there are some additional checks and code to write on our own at the application level. And with that, I would like to thank you, and I'm happy to take questions.
So before I go into questions, I'd like to welcome Mary, who is the leader of the Chicago JUG and a DataStax developer advocate. So if you have any questions about DataStax or Chicago, are there any questions about the presentation about NATS? Yes.
I have a question. You demonstrated the client setting maximum size of the queue and rejecting too many messages. The question, how it's implemented on the side of the client or server rejects this? Because I don't remember that on the protocol were some commands that could set up such parameters.
Yeah, so this is actually limit on the client side. So this is the Java client implementation that uses queues internally before publishing any message to the network. And I don't really know I'm not aware of any setting that you can configure on the server side to limit fast producers. I think that this is only the client configuration.
Thanks.
Are there questions or comments? Yes.
Thank you, great talk. So can you please describe how do you deploying this setup? You mentioned so you using only one server. Is this like bare metal server, or you deploying, I don't know, to Kubernetes? Also, what is like hardware? How much memory do you use? Probably a lot. How many requirements for CPU and other interesting stuff?
Right. Indeed, all the tests or all the results that I presented were based on running single instance NAT servers from the Docker containers. So a very basic setup. It is extremely low resource hungry, so to speak. It doesn't consume many resources. I cannot really tell how much memory does it consume, but it is happily running alongside all the other software components, so it doesn't really require a dedicated host. We also run NATs in Kubernetes clusters, but again, using a single instance. Up to this point, we didn't really have a good use case for a cluster yet.
If there are no more questions, thank you very much to our wonderful speakers. Oh, wait, Mary, and there's more questions. There's several questions. Are you ready for more questions?
Sure, hit me.
Thank you, very great talk. Does the server provide any sort of acknowledgement like the Kafka does?
So this is something that I mentioned already. It doesn't provide anything at the core NATS level. There are acknowledgements when you decide to use jet streams, but then you have to be aware that the performance is going to be worse than with what core NATS provides.
Mm-hmm. And one other question is, have you ever tested it against, for example, Red Panda, which is also claimed that have a super low latency and good throughput against, for example, Kafka?
Yeah, so first of all, we didn't. It is an implementation of Kafka in Rust, but the benchmarks are not really unified when it comes to results. So I know they promise great performance, but as far as I checked, the results are, well, they vary a lot.
Thank you.
Okay, are there more questions from anybody? Thank you very much, Piotr. And oh wait, there's Mary in the front. Questions from our guest?
Thanks for the talk, and I'm sorry I arrived late because I was at another conference. So anyway, just really quick, I might have missed too, is that what about like message logs, right? Maybe you already talked about it. I mean, this being a very simple protocol, how do you deal with message logs, right? Or do you even worry about it at all? Like you just deliver ones and, like Kafka, Pulsar, we deal with all the message logs.
Yeah, so in our particular use case, we didn't have the necessity to keep any message durable, like to store message in a persistent manner. Mm-hmm. We really had a use case to simply deliver message as fast as possible, and if client missed one or more of them, it is up to the client to resynchronize. Okay. And we already had the implementation to handle that scenario.
Okay, thank you.
Piotr, thank you. Heinz, thank you very much. And feel free to talk to them.